What if an interstellar object didn't just pass through our solar system, but reoriented itself toward Earth? In mid-December 2025, 3I Atlas did exactly that. Its anti-tail abruptly flipped, forming a dense, stable structure aimed inward, resisting the solar wind and behaving unlike any known cometary debris. At the same time, instruments detected X-ray emission, unusually high nickel concentrations, a shift toward green wavelengths, and a pattern of acceleration that gravity alone cannot explain. These signals are not random. They point to an organized, energetic process unfolding inside this object right now. In this episode, we examine what the data show, what standard models fail to explain, and why 3I Atlas has become one of the most controversial objects ever observed. If this kind of science matters to you, like and subscribe. Now, let's begin. As of December 14th, 2025, the interstellar object known as 3I Atlas can no longer be treated as a routine visitor passing quietly through the inner solar system. What began as a distant detection has rapidly turned into an object that is changing its behavior on timescales measured in hours, not weeks. Over the past day, independent observatories across multiple continents, along with several major astronomical monitoring networks, have released new imaging and spectral data. These datasets are consistent with one another, and together they describe an object undergoing an abrupt and fundamental transformation. This is not a simple case of a comet brightening as it approaches the sun or fading as it moves away. The changes being recorded point to a deeper shift in structure and activity. The shape of the object is evolving. Its surrounding cloud of material is no longer expanding in a smooth, predictable way. Instead, the system appears restless, unstable, and highly active. Images captured late on December 13th and early on December 14th show a form that departs sharply from the familiar comet model, often described as a loose mixture of ice and dust. Under normal conditions, a comet develops a coma, a diffuse envelope of gas and fine particles released as solar heat turns surface ice directly into vapor. From this coma, one or more tails form, typically stretching away from the sun. These tails are shaped by solar radiation pressure and the solar wind, and the process is largely passive. Heat in, gas out, dust pushed back. While small variations occur, the overall geometry is usually stable and easy to predict. 3I Atlas is not following that pattern. The most recent processed images reveal what astronomers have begun calling a spider-like morphology. Instead of a single, broad tail or a smooth fan of material, the object displays multiple narrow jets extending outward in different directions. These jets are short, sharply defined, and unevenly distributed around the nucleus. Visually, the structure resembles a central body with several thin legs radiating outward, rather than a single trailing plume. This appearance alone would be unusual. But what makes it more significant is how quickly it changes. The jets are not fixed in place. They do not remain steady from one observation to the next. in successive images taken only hours apart, individual jets appear, intensify, shift orientation, weaken, and then vanish. New jets emerge in different regions of the coma, creating a constantly rearranging pattern. This level of high-frequency variability is rarely seen in natural cometary activity. Such behavior suggests that the surface of the nucleus is not releasing material evenly. Instead of a uniform layer of ice slowly sublimating under sunlight, there appear to be localized active regions. These regions behave more like vents than exposed ice fields. Pressure builds beneath the surface, is released suddenly, and then shuts off. The result is a series of brief, forceful outbursts rather than a continuous flow. An everyday comparison can help clarify this behavior. Rather than a steady stream from an open valve, the object behaves more like a sealed container that releases pressure in short, violent bursts, each one altering the balance of forces acting on the system. Importantly, some of these jets have been observed pointing partially toward the sun. This is highly atypical. Solar radiation pressure should push gas and dust away from the sun, not allow material to move in the opposite direction. For a jet to project upstream against the solar wind, it must be launched with substantial force. This indicates that the activity is not driven by gentle surface evaporation alone. The ejection speeds inferred from the observations imply a process closer to propulsion than passive release. In other words, the object is actively throwing material into space with enough energy to temporarily overcome external forces. The coma itself adds another layer to the puzzle. Rather than expanding outward in a roughly spherical or smoothly elongated shape, the surrounding gas and dust show signs of organized turbulence. Subtle rotational patterns can be seen, suggesting swirling motion rather than simple radial expansion. One possible explanation is that the nucleus is rotating rapidly, causing active regions to sweep through sunlight and shadow in quick succession. Another possibility involves uneven heating across the surface, producing strong thermal gradients that drive complex flows of gas. There is also the question of internal structure. If 3I Atlas is not a solid, cohesive block, but instead a loosely bound collection of rock, metal, and exotic ices, internal stresses could play a major role. As volatile materials beneath the surface heat up, pressure may fracture a rigid outer layer. Each fracture could act as a temporary vent, releasing material explosively before sealing again or collapsing. In this scenario, the spider-like jets are not permanent features, but momentary expressions of structural failure. Measurements of activity levels support the idea that something extreme is occurring. As of December 14th, the ratio of gas to dust in the coma is unusually high. This alone would raise questions, but the chemical composition deepens the mystery. Spectral analysis shows elevated nickel levels relative to iron when compared to typical solar system comets. Under normal conditions, these metals appear in fairly consistent proportions, reflecting the composition of the early solar nebula. 3I Atlas breaks that pattern. The nickel abundance is significantly higher than expected. This raises several possibilities. The nickel could be concentrated near the surface, exposed by ongoing erosion. It could be originating from deeper layers, now being excavated by violent outbursts. Or the object may have formed in an environment with a fundamentally different chemical makeup from that of our own planetary system. At this stage, the data do not support a single clear explanation. From a structural standpoint, the object's stability is currently assessed as low. In scientific terms, this means that its form is changing too rapidly to model with confidence. Images taken in the early morning hours can differ markedly from those captured just 2 hours later. Features appear and disappear on timescales that suggest an ongoing reconfiguration of the object's surface and internal state. This rapid variability is a critical clue. Passive bodies do not behave this way. Rocks, ice, and dust responding only to sunlight tend to evolve gradually. The behavior seen here points to an active, dynamic system, one that is shedding mass unevenly and responding to internal forces as much as external ones. The spider-like shape now dominating the images may not be a stable form at all, but a brief phase in a larger, chaotic process. What this means in practical terms is uncertainty. There is no reliable way, at this moment, to predict what 3I Atlas will look like tomorrow. Continued outbursts could reshape the coma into a ring-like structure, a spiral pattern, or even lead to partial fragmentation of the nucleus itself. The object is in motion not only through space, but through a rapid sequence of physical states that resist simple forecasting. Yet within this instability, not every feature behaves the same way. Amid the flashing jets and the constantly shifting structure near the nucleus, one component has persisted. It has not faded, flickered, or dissolved. While the activity close to the core appears chaotic and transient, this feature remains intact. And in many ways it is even more difficult to explain than the spider-like eruptions themselves. As attention shifts away from the chaotic coma and toward the larger scale structure surrounding 3I Atlas, a form appears that should not exist in its current configuration. The jets are scattered, explosive, and directionally unstable, producing the spider pattern already described. Yet, embedded within this disorder is a separate structure that is organized, persistent, and coherent. It is this contrast that has drawn intense scrutiny from multiple researchers, including Avi Loeb and several independent analysis teams. The structure is known as the anti-tail. Unlike the jets, the anti-tail does not pulse or blink in and out of view. It does not fragment or dissolve as the hours pass. It holds its shape. It occupies a clear and well-defined region of space. And most notably, it points in a direction that challenges conventional expectations. This is not a fleeting artifact of image processing or a trick caused by viewing angle. The data indicate that it is a physical feature, made of matter, behaving in a way that standard comet models struggle to accommodate. This raises an immediate question. If the jets represent the active engine of the object, violently ejecting material from the surface, then what exactly is the anti-tail? Is it a byproduct of that activity? A form of exhaust? Or is it something structurally and dynamically separate? The observations from December 14th provide an important clue because they document a change that should not have occurred if this feature were ordinary cometary debris. Under typical circumstances, a comet's tail geometry evolves in a predictable way as it passes perihelion, the point of closest approach to the Sun. The orientation of dust features adjust smoothly as solar radiation pressure and orbital motion interact. In many cases, an apparent antitail can form. This happens when Earth crosses the comet's orbital plane, allowing observers to see the dust trail edge on. The result is a spike-like feature that appears to point toward the Sun, even though the material itself is still trailing behind the comet along its orbit. It is a visual effect, not a physical reversal, for 3I Atlas. That explanation no longer fits the data. The antitail has not merely appeared due to changing perspective, it has rotated. After perihelion, instead of dispersing or flattening into a faint dust sheet, the structure maintained its coherence and flipped its orientation relative to the Sun. This behavior suggests that the material involved is not responding to sunlight in the way fine dust normally would. Solar radiation pressure is highly effective at pushing small particles, micron-sized grains, comparable to smoke or soot, are easily accelerated and spread out, forming broad, diffuse tails. If the antitail of 3I Atlas were made of such material, it should have been quickly distorted and blown back as the object moved through perihelion. Instead, the feature remains tight, narrow, and sharply defined. This resistance to solar influence is a critical observation. It implies that the particles composing the antitail are large and massive enough that the pressure of sunlight has little effect on their motion, rather than behaving like a cloud of dust. The structure behaves more like a collection of solid objects following a shared trajectory. The reflectivity of the feature further supports this interpretation. It reflects sunlight efficiently, suggesting surfaces that are compact rather than diffuse. In recent reports, the antitail has been described not as a stream, but as a swarm. This choice of language is intentional. A stream implies continuity, a flowing medium. A swarm implies a grouping of discrete bodies, each maintaining its own integrity while moving together. This distinction matters because it changes how the structure interacts with external forces. A swarm of heavy fragments would respond very differently to solar radiation than a plume of fine dust. The size of these fragments remains uncertain, but the physical implications are already significant. The material could consist of pebble-sized clasts, larger rocky chunks, or refractory fragments capable of surviving intense heating without rapidly vaporizing. These would not be easily dispersed. They would follow more ballistic paths, shaped primarily by gravity and the object's original ejection dynamics rather than by sunlight alone. This creates a striking duality in the behavior of 3I Atlas. Near the nucleus, the object appears volatile and unstable, releasing gas and fine material in explosive bursts. Further out, it leaves behind or carries with it a structure that is quiet, dense, and persistent. The spider-like chaos of the coma contrasts sharply with the silent order of the anti-tail. Together, these two behaviors define the current observational picture. Understanding the nature of this object, therefore, requires understanding both what is erupting outward and what is remaining organized behind it, or possibly even ahead of it along its path. The anti-tail is not simply an afterthought. It is an integral part of the system's mass loss and momentum balance. Its behavior suggests that whatever is happening on or beneath the surface of 3I Atlas is producing not only gas and dust, but solid material in a structured way. The fact that this swarm has flipped orientation after perihelion is especially important. The flip indicates that the structure is dynamically linked to the object's motion through space, not just passively dragged along. It maintains integrity through a period when forces are strongest and most disruptive. That persistence alone sets it apart from ordinary cometary features. At this stage, the anti-tail can no longer be dismissed as a visual illusion or a minor anomaly. It is a stable, evolving component of the system, one that appears to follow a coherent path rather than dispersing randomly. While the spider-like jets remain the most visually striking feature of 3I Atlas, they may only reflect surface-level activity. The structure forming beyond the coma suggests a deeper process, one that shapes not only how material is released, but how it moves through space. To understand what this structure is doing, attention must shift from appearance to motion. A closer examination of positional and kinematic data adds another layer to this already complex picture. As of December 14th, 2025, 3I Atlas is located at a distance of approximately 270 million kilometers from Earth. This is not close in everyday terms, but in astronomical observation, it places the object well within the range where fine structural details can be tracked with high confidence. At the same time, the object is moving through space at a velocity of roughly 63.7 kilometers per second, a speed shaped by both its interstellar origin and its recent passage through the Sun's gravitational field. What is especially notable is that the anti-tail, the dense swarm-like structure previously described, is not lagging passively behind. Measurements indicate that it is being accelerated along with the main body. This persistence, after perihelion, combined with the current orbital geometry, means that by approximately December 19th, the line of sight from Earth may align closely with the axis of this structure. This does not imply any risk of impact. The distances involved remain immense, and there is no scenario in which Earth is threatened by a collision. What it does mean is that observers will be positioned to view the swarm nearly head-on. From a scientific standpoint, this is a rare and valuable configuration. Instead of seeing the structure from the side, compressed by perspective, instruments may be able to probe its depth, density, and internal coherence. In effect, researchers will be looking directly into the structure rather than across it. This alignment offers an opportunity to test competing interpretations, but it also amplifies the central mystery. If the anti-tail consists of heavy, rocky fragments, a fundamental question arises. Where did this material originate? Classical comets are dominated by volatile ices mixed with fine dust. They are not known for releasing large quantities of solid rock. For 3I Atlas to be producing a massive swarm of dense objects, its internal structure must be different from the standard comet model. One possibility is differentiation. The object may contain a rocky interior beneath a volatile, rich outer layer. As the outer layers erode or fracture, more durable material could be exposed and released. Another possibility is the presence of a rigid crust composed of refractory material, breaking apart in sections rather than dissolving gradually. In this scenario, the swarm would represent fragments shed from this outer shell, rather than debris excavated from deep within. Both interpretations require a level of internal organization that goes beyond a loosely bound mixture of ice and dust. The optical properties of the swarm deepen the puzzle. Observations indicate high reflectivity. This immediately rules out several common materials. Carbon-rich asteroids, which are abundant in the solar system, tend to be dark and absorb light rather than reflect it. Fine dust grains also scatter light in a diffuse way, producing broad, faint features rather than sharp, bright structures. Ice, by contrast, can be reflective. But ice exposed to intense solar heating should sublimate rapidly or be dispersed by radiation pressure. The swarm associated with 3I Atlas does neither. It remains bright and compact. This points toward materials that are both reflective and resistant to sublimation. Refractory compounds, metallic fragments, or mineral-rich aggregates are among the remaining candidates. Such materials can survive high temperatures and maintain structural integrity over long distances. Their presence would again imply an origin very different from that of a typical comet. Recent reports describe the shape of the antitail as resembling a droplet. This term is not used casually. In physical analysis, a droplet shape often implies the action of cohesive forces or a history of directional shaping. In fluids, such shapes arise from surface tension. In solid particle systems, they can emerge when fragments are released in a focused stream rather than isotropically in all directions. If solar, wind, and radiation pressure were the dominant sculpting forces, the structure should appear elongated and diffuse, stretched away from the sun. Instead, the droplet-like form suggests that the shaping occurred at the moment of ejection. The force that expelled these objects was likely directional, concentrated along a specific axis. This again distinguishes the antitail from the chaotic spider jets, which erupt in many directions and change rapidly over time. At this point, it becomes useful to consider the system as a whole. At the front, near the nucleus, there is an environment of instability. Gas and fine material erupt explosively, driven by internal pressure and rapid heating. Behind, or possibly slightly ahead, depending on geometry, there exists a heavy, coherent structure that does not respond strongly to external forces. One component behaves like a volatile engine. The other behaves like a wake composed of solid matter. In classical terms, both features would be grouped under the label of a comet, yet the coexistence of these behaviors strains that definition. The system does not resemble a simple icy body gradually eroding under sunlight. It behaves more like a structured object undergoing controlled, or at least directional, mass loss. This tension between classification and observation is at the heart of the current debate. The significance of the recent flip in the anti-tail becomes clearer in this context. The flip indicates that the orientation of the swarm is tightly coupled to the orbital dynamics of the main body. It moves as though it were an extension of the nucleus rather than an independent trail of debris. Smoke disperses. Dust spreads. This structure does neither. It reorients as a unit. Such behavior adds to a growing list of anomalies highlighted by Avi Loeb and others. In natural systems governed by gradual processes, changes tend to be smooth. Transitions occur continuously as conditions evolve. What is observed here is different. The flip represents a discontinuity, a sudden change in orientation that coincides with the object's passage through the region of strongest solar gravity. This suggests a threshold was crossed, triggering a different mode of behavior. At present, the anti-tail stands as the strongest evidence that 3I Atlas is not a loosely bound, fluffy aggregate. It appears to be a solid, dense body capable of shedding large debris fields that remain coherent over distances of millions of kilometers. As Earth's viewing angle improves, approaching December 19th, measurements of brightness, variation, and spatial extent may allow researchers to estimate the density and mass distribution within the swarm more accurately. Yet, structural anomalies are only part of the story. If the spider-like jets function as an engine, and the swarm represents the wake left behind, then attention must turn to the source of energy driving this system. This requires looking beyond visible light, into parts of the spectrum that are not directly seen by the human eye. Recent observations have detected something exceedingly rare for cometary objects: X-ray emissions. Under normal circumstances, comets are cold bodies. They reflect sunlight and emit infrared radiation as they warm, but they do not generate high-energy photons. X-rays indicate energetic interactions, typically involving charged particles, strong magnetic fields, or high-temperature processes. The detection of X-rays immediately elevates the significance of the object. It implies that 3I Atlas is interacting with the solar environment in an unusually intense way. This could involve the stripping of electrons from atoms, the acceleration of charged particles, or rapid chemical reactions releasing energy far beyond what simple sublimation would produce. At the same time, changes in visible color have been recorded. The coma has shifted toward a distinct green hue. This is not a vague coloration, but a specific spectral signature associated with diatomic carbon, a molecule consisting of two carbon atoms bonded together. This molecule emits green light when excited by solar radiation. Its presence indicates active chemical processes venting carbon-rich gases into space. Green comets are not unheard of, but the context matters. When combined with X-ray emissions and high nickel abundance, the green coloration becomes part of a broader pattern. It suggests that the object's surface, or interior, is undergoing chemical transformations as it travels through the inner solar system. the composition of the emitted material is changing, implying that new layers are being exposed or new reactions are being triggered. Together, these signals point toward what can be described as a chemical engine, not an engine in the mechanical sense, but a system in which stored chemical energy is being released in a controlled or semi-controlled way. The spider jets may represent the exhaust of this process. This naturally raises a set of unresolved questions. What reactions are driving it? Why does nickel appear in such high concentrations? And why are X-rays present at all? These questions do not yet have definitive answers, but they do define the next step forward. If the structure, motion, and energy output of 3I Atlas are linked, then the most direct way to probe the engine itself is through the light it produces. To move beyond surface behavior and visible structure, the analysis must turn towards spectral data. Physical motion shows how the object responds to forces. Light reveals what it is made of and how energy is being released. For 3I Atlas, this shift in focus exposes internal processes that are not only unusual, but energetically intense. The most striking signal to emerge from the latest observations is the detection of X-ray emissions. This alone sets the object apart. Comets are, by nature, cold bodies. They are composed largely of ice and frozen gases. They reflect sunlight and, as they warm, emit infrared radiation. Under normal circumstances, they do not generate X-rays. When X-rays are observed in association with a comet, the source is almost always indirect. The process responsible is known as charge exchange. In this interaction, highly charged ions carried by the solar wind collide with neutral atoms in the comet's coma. During the collision, the ions capture electrons from the neutral atoms. As these electrons settle into lower energy states, X-ray photons are released. The comet itself does not need to be hot. The energy comes from the solar wind. This process is well understood, but its efficiency depends on one critical factor: the density of gas surrounding the comet. A faint, thin coma produces weak X-ray signals. A strong X-ray signature implies a thick and highly active gas envelope. In the case of 3I Atlas, the observed emission is intense. It confirms that the coma is not a tenuous cloud, but a dense and expansive region where interactions with the solar wind are frequent and energetic. This reinforces earlier assessments that gas production is exceptionally high. What is remarkable is the scale of this activity relative to the size of the nucleus. Based on brightness and emission strength, the volume of gas being released rivals that of comets known to be significantly larger. This suggests that whatever process is driving the outgassing is unusually efficient or unusually energetic, or both. While X-rays reveal the intensity of interaction, the visible spectrum provides insight into composition. Recent imaging shows that the coma has developed a pronounced green tint. This coloration is not arbitrary. It corresponds to emissions from diatomic carbon, a molecule consisting of two carbon atoms bonded together. When this molecule is excited by solar radiation, it emits light in the green portion of the spectrum. Green comets are not unprecedented. However, The context and timing of this color shift are critical. Prior to perihelion, 3I Atlas exhibited a reddish hue. Red coloration in cometary bodies is commonly associated with complex organic compounds known as tholins. These materials form when simpler molecules are exposed to cosmic radiation over extremely long periods of time. They accumulate on surfaces in the outer regions of planetary systems. Red, in this context, is a marker of age and long-term exposure. The transition from red to green signals a physical change. The outer, radiation-processed layer has been removed. Solar heating near perihelion has stripped away this older crust, exposing fresher material beneath. The green emission indicates that volatile carbon-based gases from the interior are now venting into space. This is not merely a change in appearance. It is evidence of resurfacing and renewal. What makes this observation even more intriguing is where the green emission is strongest. Instead of being confined to the immediate vicinity of the nucleus, the diatomic carbon signature is intensifying within the antitail. This challenges earlier assumptions. The antitail had been interpreted primarily as a collection of heavy, inert fragments. If those fragments were dry rock, they would not produce a strong molecular emission signature. The presence of green emission implies active outgassing. The fragments within the swarm are not chemically dormant. They are releasing gas of their own. This forces a reassessment of the swarm's nature. It is not simply debris shed and left behind. It is a collection of objects that retain volatile components and continue to interact with solar radiation. In typical comets, tails follow well-defined patterns. Dust tails appear yellowish or white due to reflected sunlight. Ion tails appear blue due to ionized gases interacting with the solar wind. A green-dominated feature, especially one associated with a dense swarm, does not fit neatly into either category. It suggests a hybrid structure where solid fragments and active chemistry coexist. Spectral analysis extends beyond color alone. Detailed measurements reveal the presence of several specific compounds. Methanol, known chemically as methyl alcohol, has been detected. Hydrogen cyanide, a molecule composed of hydrogen, carbon, and nitrogen, is also present. Carbon dioxide appears as well. Each of these compounds is volatile, but each responds differently to heat. Methanol sublimates at lower temperatures than water ice. Hydrogen cyanide requires slightly more energy. Carbon dioxide occupies a different thermal range altogether. The simultaneous presence of these molecules implies that the object contains layered or mixed reservoirs of volatiles, each activating as temperature conditions change. This supports the idea of a complex internal structure rather than a uniform mixture. Among these detections, one element stands out as particularly puzzling: nickel. Elevated nickel signatures have now been confirmed across multiple datasets. In the solar system, nickel is typically found alongside iron. The two elements form together in stellar environments and tend to remain associated during planetary formation. A high ratio of nickel relative to iron is unusual. Such a ratio implies a formation environment unlike that of our own system. It suggests that 3I Atlas originated in a region where chemical conditions differed significantly. This could involve variations in temperature, pressure, or elemental abundance during formation. It could also indicate that differentiation processes separated heavy elements in ways not commonly observed here. The presence of nickel is also relevant to energy processes. Nickel-rich materials can influence catalytic reactions and thermal behavior. While no direct conclusions can yet be drawn, the combination of nickel, volatile organics, and high-energy emissions points toward a chemically active system operating under extreme conditions. Methanol and hydrogen cyanide are often described as prebiotic molecules. In astrobiology, they are considered building blocks for more complex chemistry. In this context, however, their importance lies in their physical properties. Each compound vaporizes at a different temperature as heat penetrates deeper layers of the object. Different substances are released in sequence. This staggered release provides a potential explanation for the observed variability. Instead of a single phase change, the object may be undergoing multiple overlapping transitions. As one reservoir is depleted, another becomes active. This would naturally produce episodic outbursts, changes in composition, and shifts in emission across the spectrum. Taken together, the spectral data paint a picture of an object that is not only structurally complex, but chemically layered. Energy is being released through interactions with the solar wind, through chemical reactions, and through the progressive exposure of interior materials. The spider-like jets, the active swarm, and the evolving spectrum are not separate mysteries. They are interconnected expressions of the same underlying process. At this stage, the evidence points toward a chemical engine operating within 3I Atlas, not a single reaction, but a network of reactions, each triggered under specific conditions. The jets may represent the visible exhaust. The swarm may be composed of fragments carrying their own volatile reserves. The light emitted across the spectrum reveals how energy flows through the system. The remaining question, and the one that now demands closer attention, is what combination of reactions can produce this behavior? The presence of nickel, the emission of X-rays, and the release of volatile compounds at different temperatures all suggest that this engine is running on an unusual fuel mixture. Understanding how these components interact will be essential to explaining what 3I Atlas truly is and how it continues to evolve as it moves away from the Sun. The fact that all of these substances are being detected at the same time, volatile compounds alongside high-temperature metal emissions, places a strong constraint on how the interior of 3I Atlas must be organized. This is not a body built like a clean stack of layers, with fragile ices neatly separated from heavier materials. The evidence points towards something far more disordered. Instead of a layered structure, the interior appears to be mixed, uneven, and chemically chaotic. A useful way to picture this is not as a layered cake, but as a marbled one. Volatile compounds that freeze at extremely low temperatures are embedded directly within a matrix of rock, metal, and refractory material. Heavy elements such as nickel are not confined to a deep core. They are distributed throughout the structure. When heat penetrates this mixture, the response is not gentle or uniform. It is abrupt and violent. This internal disorder offers a plausible explanation for the spider-like jets observed earlier. If pockets of highly volatile compounds, such as hydrogen cyanide, are trapped within rigid material, they behave very differently than surface ice. When exposed to increasing heat, they do not slowly sublimate. Pressure builds rapidly. Once the surrounding material fails, the release is explosive. Each pocket acts like a localized pressure bomb, ejecting gas and entrained material in short. Intense bursts. This type of behavior naturally produces episodic outgassing rather than a steady flow. It also explains why the jets appear suddenly, change direction, and then vanish. The chemical engine driving this activity is unstable by nature, not because of a single reaction, but because the fuel is poorly mixed. Different compounds respond to heat at different thresholds. As a result, the engine sputters. It surges and backfires rather than running smoothly. When this framework is applied to the broader coma behavior, several previously puzzling observations begin to align. The swirling, cyclone-like motion detected in the gas envelope is consistent with uneven thrust. If one region of the nucleus is rich in carbon dioxide, while another contains higher concentrations of methanol or hydrogen cyanide, each region will activate at a different point along the object's trajectory. Gas release becomes spatially and temporally uneven. This uneven outgassing produces asymmetric forces. The object is not simply losing mass. It is being pushed by its own exhaust. Each outburst adds a small impulse. Over time, these impulses accumulate. The result is motion that deviates from what gravity alone would dictate. This brings the analysis to the next major anomaly: movement. 3I Atlas is not only chemically complex and structurally unstable, it is dynamically misbehaving. Jets, expanding gas, interactions with the solar wind, and the release of solid debris all exert force on the nucleus. These forces do not cancel cleanly. They push in different directions at different times. Astronomers calculate the expected position of an object like this using gravitational models. These models account for the pull of the Sun and planets with extraordinary precision. Under normal circumstances, the predicted path and the observed path align closely. For 3I Atlas, they do not. The object consistently appears slightly displaced from where gravity alone says it should be. These deviations are known as non-gravitational accelerations. They are abbreviated as NGAs. Small NGAs are common in comets and are usually attributed to outgassing. What makes 3I Atlas stand out is the magnitude and complexity of these accelerations. As of December 14th, 2025, the values exceed what is considered typical, even for highly active comets. To quantify these forces, astronomers use three parameters: A1, A2, and A3. Each corresponds to a different direction of force. A1 represents radial acceleration, pushing the object directly away from the Sun. This is usually the dominant term and reflects the basic rocket effect of sunlight-driven outgassing. A2 measures transverse acceleration, acting along the direction of the orbit. This component alters the object's speed along its path. A 3 represents normal acceleration, acting perpendicular to the orbital plane. This component can tilt or warp the orbit over time. For most comets, a 1 dominates. A 2 and a 3 are present but relatively small. They tend to average out due to rotation. For 3I Atlas, this balance is disrupted. Updated calculations show that A2 and A3 are unusually strong. The object is not just being pushed outward, it is being steered sideways and vertically relative to its orbital plane. This creates a contradiction when compared with observed morphology. Normally, strong non-gravitational accelerations are associated with rapid rotation. A fast-spinning nucleus sprays jets in many directions, like a rotating sprinkler. This rotation blurs structural features and produces smooth, averaged forces. In such cases, tails appear diffuse and symmetric. 3I Atlas does not fit this pattern. The spider jets remain sharply defined. The anti-tail remains coherent. The coma retains organized structure rather than dissolving into a uniform haze. If the nucleus were spinning rapidly enough to generate the observed NGAs through rotation alone, centrifugal forces would disrupt these features. That is not what is seen. This suggests that the forces acting on the object are not being averaged out by rotation. Instead, they remain directionally biased. The thrust is organized. Even if the underlying chemistry is chaotic, the object is being driven in specific directions for sustained periods, rather than randomly sprayed in all directions. Additional imaging from December 14th provides further context. The coma is not centered symmetrically around the nucleus. The brightest region, associated with the nucleus itself, appears compressed and offset within the surrounding gas envelope. This displacement is a visual marker of imbalance. It indicates that gas production is stronger on one side than the other, pushing the nucleus away from the center of its own coma. This offset aligns with the presence of strong A2 and A3 components. It shows that the non-gravitational forces are not theoretical constructs derived only from orbital math. They are visible in the structure of the coma itself. The object is physically being pushed off-center by its own activity. Taken together, these observations reinforce a consistent picture. 3I Atlas is not a passive body responding gently to solar heating. It is an active system with a chemically mixed interior, producing uneven outgassing, shedding solid and volatile material, and experiencing sustained non-gravitational forces. These forces are strong enough to measurably alter its trajectory, yet organized enough to preserve distinct structures. The spider jets, the active swarm, the chemical emissions, and the anomalous motion are not separate problems. They are different expressions of the same underlying instability. The object is being driven by an internal engine that does not burn smoothly. It surges, misfires, and pushes unevenly, imparting momentum in unexpected directions. At this point, the focus must shift fully to motion. The structure and chemistry explain how forces are generated. The next step is to understand how those forces translate into the observed deviations from a gravity-only path. The non-gravitational accelerations are the measurable consequence of everything observed so far, and they represent one of the most concrete ways to test competing models of what 3I Atlas truly is. The current imaging data offer a particularly revealing geometric detail. The coma surrounding 3I Atlas does not expand evenly around the nucleus. Instead, the luminous envelope appears shifted to one side, as though the central source of light were pressed against the inner wall rather than suspended at the center. This offset is not subtle. It is measurable, persistent, and consistent across multiple observations. This asymmetry carries physical meaning. A coma expands symmetrically only when gas is released uniformly across the surface. What is observed here confirms the opposite. Outgassing is not global. It is localized. The jets originate from specific regions on the surface, and those regions do not consistently align with the direction of solar heating. The sun is not dictating where material escapes. Internal structure is. The displaced envelope is therefore a direct manifestation of asymmetric thrust. 3I Atlas is not merely losing mass, it is actively pushing itself sideways. The brightness variations seen frame by frame reinforce this interpretation. These fluctuations are not random noise or imaging artifacts. Each spike in brightness corresponds to a fresh ejection of material, and every ejection carries momentum. Momentum does not vanish. When mass is expelled in one direction, the remaining body is pushed in the opposite direction. Over time, repeated impulses alter the trajectory. In effect, the object behaves like a natural rocket, one with an unstable throttle and an uneven exhaust. The thrust is intermittent, the direction varies, but the cumulative effect is measurable motion. This leads directly to the implications for trajectory. Avi Loeb and others have emphasized that the probability of this motion being purely random is low. When multiple indicators are considered together, a pattern emerges. The flip of the anti-tail, the orientation of the jets, including some directed partially toward the sun, and the unusually strong transverse and normal acceleration parameters all point to a complex motion vector. This motion is not simple tumbling, nor is it aimless drift. It resembles maneuvering in a physical sense, not implying intention, but reflecting a system responding dynamically to multiple interacting forces. The solar wind plays a role. Internal pressure plays a role. Structural constraints within the nucleus play a role. The result is what can best be described as organized asymmetry. Random processes tend to blur structure. Noise averages out. What is seen here does not resemble static. It retains form. The jets maintain directionality. The swarm remains coherent. The asymmetry persists over time. This indicates that the forces involved are not evenly distributed or rapidly randomized. One of the most telling details is the orientation of the jets themselves. In standard cometary activity, jets tend to align roughly toward the sun. Heat drives sublimation, and gas escapes most readily from sunlit areas. In 3I Atlas, many jets diverge from this expectation. Their directions suggest that internal heat distribution lags behind surface illumination, or that the pathways for gas escape are constrained by physical features. If the nucleus is fractured, those fractures dictate where gas can travel. The sun may provide the energy, but the structure determines the outcome. Cracks, voids, and rigid boundaries channel the flow. In such a system, the direction of jets reflects internal geometry more than external illumination. This observation ties directly into the rotation problem. High thrust typically generates high torque. Torque leads to rapid spin-up. In loosely bound cometary nuclei, this process often ends in fragmentation. The body cannot withstand the stress and breaks apart. Yet 3I Atlas remains intact, despite accelerating, pulsing, and ejecting material violently. It has not disintegrated. The spider jets remain distinct. The antitail retains coherence. The coma does not dissolve into a uniform cloud. This combination is paradoxical. Instability is present, but it is contained. The most straightforward implication is internal strength. The nucleus is not behaving like a fragile rubble pile. It appears capable of absorbing stress without catastrophic failure. This suggests a body with significant mechanical integrity. It may be monolithic, or at least composed of large, tightly bound sections rather than loosely aggregated grains. Such a structure aligns with the swarm interpretation. If outer layers are being shed while the core remains intact, the system would produce heavy fragments without immediate total disruption. The core would persist, continuing to drive activity even as material is lost. As orbital updates continue, the cumulative picture becomes difficult to ignore. The list of anomalies is no longer short. It includes spider-like jets driven by episodic outbursts, a coherent anti-tail composed of heavy active fragments, detectable X-ray emissions, a pronounced shift to green diatomic carbon signatures, elevated nickel abundance, an offset nucleus within the coma, and non-gravitational accelerations that exceed typical ranges. Each of these features can be examined in isolation. None, by itself, demands a radical explanation. But taken together, they form a dataset that resists easy categorization. The question becomes not whether each anomaly can be explained, but how many exceptions a simple model can accommodate before it ceases to be simple. Scientific interpretation relies on parsimony. The simplest explanation consistent with the data is preferred, but simplicity is not defined by familiarity. A model burdened with numerous caveats, adjustments, and special conditions may be less parsimonious than one that starts from a different premise. This is where the current debate resides. Some researchers maintain that all observed features fall within the extreme but natural range of cometary behavior. Others argue that dismissing the coherence and organization seen here requires ignoring key aspects of the data. The disagreement is not philosophical. It is empirical. Official assessments classify 3I Atlas as a natural object. At the same time, independent analyses urge caution, emphasizing that classification should follow evidence rather than precedent. The verdict has not been reached. What is clear is that additional observations will be decisive. With high-resolution instruments such as the Hubble Space Telescope and the X-ray Imaging and Spectroscopy mission scheduled to observe this object, the available data will soon expand dramatically. These observations will test existing interpretations and either reinforce or challenge current assumptions. At this stage, the investigation stands at a threshold. The physical structure, chemical composition, and dynamic behavior of 3I Atlas have been mapped in unprecedented detail. The implications of these findings now come into focus. The final question remains open, awaiting further evidence and careful analysis. What exactly is 3I Atlas?